Alicia.
Great. Well, thank you for that. Thank you for that great introduction, Sean, and I appreciate the invitation to talk about some of this work. And it's always interesting to see over time how military operations research in the data science community adjust to the emerging and continued needs in some cases for our military services. So really, really excited to present this and really for feedback and questions from the audience as well. So I'll roll through this and I don't see a chat thread on my end. So if there is a chat and there's a question, if you guys could just let me know, I'll answer the question. So great. This is my agenda for today. I'm going to talk a little bit about this problem that we're helping to solve. I'll talk about how we're approaching it from both a functional analysis and a modeling standpoint. And I'll show some initial results that we have. There's a whole lot of results, so I'm not able to show all of them. But I will give you guys a taste for what we're looking at. And as I mentioned, if you have a question during, feel free to ask. I might be answering that question later on in the presentation. If I am, then I'll kind of defer to later and then make sure I answered your question later. If not, we can answer your questions at the end too. So we're dealing with a pretty complex problem here. When we talk about large-scale force movement, arrival and assembly in an area of operations, and really focusing on getting a capability in place that you need multiple units over long distances to get there. So it's a complex problem, and what we're doing is we're approaching this with, in this case, the Marine Corps, by helping them be able to evaluate many different types of scenarios. So a very broad range of scenarios. These scenarios look at different levels of forces. It could be very large force. In this case, in this scenario that I'm going to be using to talk through the modeling and our approach, we're using one large force. And so we could look at force movement from one or more locations. We're dealing with different types of shipping. We're dealing with ships that are pre-positioned around the globe, other ships that are need to move to the unit origin location or close to the origin location, pick units up and move them into theater. And we're also talking about airflow, so aircraft movement. And we'll talk a little bit more about that, but that's both strategic air and unit aviation assets. And then we need to be able to look at the necessary level of detail to really understand what are the impacts of this movement of the force and all the operations that have to happen to marry up people with all their equipment to the point where they can say that they're fully capable. So there's several modeling considerations that we have to consider. And we have to look at, hey, what's the best level of resolution to make sure, we can give the force planners all the information they need while still being able to run a model in timely fashion. It's something that we always run into as modelers, right? We have to look at different levels of units. So we have to be able to handle that, which includes parent-child relationships. It includes aggregation and deaggregation of units so that units can move in packages while maintaining some level of integrity. And then we also have to look at different types of resources that are used. So if we're going to provide a picture of not just the force that's moving, but all the supporting assets and people, equipment that have to be there to help with that, they add to the footprint. So how can we minimize those resources, or what's the right amount? We also look at different movement timelines. So different units have different priorities to get into the area of operations at different timeframes. And so there's a time scale, and then there's priority of units, and those have to be considered in a sequencing approach to figure out how best to get them into theater, and then what transportation assets would be best for them to be on to support that sequencing. And then we have to look at, what are we optimizing? Okay, what are we smoothing? So we want to make sure that we can close the force as quickly as possible, considering unit integrity. So we want to maybe get an infantry unit up and running first with our weapons company, maybe before we bring in another type of unit, right? So we have to optimize the closure times, and that also includes minimizing the gap between when forces arrive in different what we call movement groups, which we'll get into later. And then we have to be able to support scenarios that look at traditional employment and future employment concepts. So yeah, it's a complex problem with a lot of modeling considerations. From a readiness standpoint, we're looking at this as, hey, how quickly can you get the capability up and ready to move forward into the fight or to support the mission? And we measure this in terms of the closure time, or the time to get that capability, and the size of the footprint needed to support that capability. A little different way of looking at readiness instead of just availability. So spent a lot of time on that slide just to kind of help us frame the problem. I'm going to move through some of these other slides a little bit more quickly. I'll spend a little bit of time on this one. So this is, once again, looking at this high-level scenario in an operational view type of picture. So in this scenario that I'm talking through, we're looking at what we call a baseline Marine Expeditionary Force. So it's a very large force for the Marine Corps. They're moving from continental United States, from their point of origin to their points of embarkation. They're moving into theater through an airfield, which we're showing here. They're moving via strategic lift, and they're moving both their passengers and cargo that way. And they're also using what we call a flight ferry, basically taking their fixed wing assets and moving them, tilt rotor assets, and moving them into theater. There's also 2 MPS, Maritime Prepositioning Force squadrons. And so a whole bunch of ships that are preloaded. We have 3 berthing spots. We have 8 what we call black bottom ships. So there's a lot of movement via surface into theater. And then once you get into theater, there's multiple processes where and locations where units and cargoes then disperse to. So they could be taken to different staging areas. It could be they move to their final, what we call arrival and assembly operational element. That's where they organize for forward movement. So if from an Army term, this is like the RSO&I process. For the Marines, we call it arrival and assembly. So a cool thing about this scenario is we have a baseline scenario, and then in the modeling capability, we have to be able to run a bunch of different what we call excursions to the baseline scenario. So we might have 3 piers, or we might say, hey, what if we increase that to 4, 5, or 6 piers? Does that help our closure time? Or if we change sequencing of the units, does that help? Or if we add more resources like material handling equipment or material handlers or drivers or wreckers, does it reduce the total force closure time? So this really allows us to look at where are the bottlenecks, what's the best lift strategy, and what's the best cargo and equipment sourcing strategy once we get into theater. Is it from pre-positioning equipments? Do you gain anything by adding another black bottom ship? Or do you gain more by adding more strategic lift? So there's a lot of really interesting trade-offs we can get into within this scenario. So we decided to address all the modeling considerations. Our modeling approach was to put together a suite of modeling and simulation components, I'd call them, or capabilities. So I'll get into these a little bit more detail. This is my general flow just to kind of explain to you what happens. And so I'm going to start from the upper left-hand side. We have a data management capability. We bring in data from the individual planners. The users will provide data to define a scenario, and they might provide some additional data that is not available in Marine Corps authoritative sources. We'll bring in data from different authoritative sources, like from the prepositioning as loaded data on the prepositioning ships, so that we understand what cargo and supplies are available. And we have some other data sources that we use to basically provide the equipment density list for the units that are selected, things like that. All this feeds into what we call our input data miner. And the input data miner's responsibility is to provide the interface between the users, the data, and to run these things down below, which we call estimators. And so we have multiple estimators that help us do a couple things. One is to pre-process information for some of the other modeling components. And they also provide direct output. So for example, how many sailors and Marines do you need on the MPF ships? That's the offload preparation party, or OPP. And which ships should they be on? How do you account for them? Force flow estimator gets into the sequencing problem. Okay, how do you best sequence and basically put the units of cargo and people onto these aircraft and onto the ships? So how do you not necessarily stuff the aircraft into ships, but how do you sequence them, and then how do you organize them into the right packages on those aircraft? We also have a connector type of capability where we look at, hey, what's the capacity of all these connectors that you have for your in-stream movements? So if you don't have a pier and you have to have a ship at a certain standoff distance, what are the capacity of those causeway ferries or those connectors, those distribution assets? And how much that kind of helps determine basically the flow of equipment from ship to shore. And then we have the arrival and assembly resources. So these are the people, the material handling equipment, the vehicles, the drivers, the resources that you have in the area of operations to actually move stuff to the final destination. So all that provides initial input into, for this scenario, this large MEF side scenario, with a very traditional arrival and assembly method, into what we call the arrival and assembly queuing model. And we'll get into this a little bit more later too. This is basically a complex series. It's a stochastic model, multiple queues. And once the equipment gets into theater, it helps figure out how best to process that through to the final destination. And it allows us to evaluate where are the bottlenecks within theater based on a combination of the volume of arrival at the different points of entry and the number of resources that you have at different nodes within the arrival assembly area. We also have a node size estimator that looks at, okay, now what's the size of the footprint at each of these nodes over time? So you can see how the footprint will expand and contract and what that steady state amount is. So you know how much real estate that you need within the area just to get everybody in theater and ready for movement forward as a capability. And then on the output side, we have what we call the output data miner, which helps provide, it basically takes all the modeling results, all the modeling output, combines it with the input, the scenario input data, and then it publishes this, what we call a force closure analysis handbook. So a lot going on there, and a lot going on in this picture too. This kind of helps us focus more on, the scenario part and the input and the output data miner. So from the input data miner, what we needed to do is we needed to reflect back to the user or to the person who's setting up the scenario some basic information so that they can confirm that the scenario is behaving correctly. So what we do is we have user will enter the scenario information, and this could be an analyst. Mostly it's an analyst right now, but the analyst would enter this, and then we'd run the estimators, and then we'd reflect back to them what we call movement group templates. So they could see generally, based on the force flow estimator, how units were sequenced and moving into theater by movement groups. And then we also get into ship templates. So we could say, okay, these are the ships, and this is when they would be offloaded. And then we look at what we call arrival and assembly templates. So this is the initial resource laydown. We do have a capability for the resources to dynamically be redistributed every 24 hours. So, but we want to show them the initial laydown just so they get a good sense for it's a good starting point. And then what we do is there's a lot of interfaces you can imagine between the scenario setup and all that data, and then the multiple runs with the estimators and the AEQM to come up with the results. So the IDM database is important for us to be able to synthesize that data in the output data miner and to produce that handbook. So, all right, going back now to the scenario. So we just talked a little bit about the modeling approach, the components. that we use to model this. Looks kind of basic, but there's a lot going on within each of these. So we have one area of operations in this scenario. We have a large unit, a Marine Expeditionary Force. It's moving from their point of origin through their points of embarkation. And from there, they're either going through an aerial port, picking up strategic lift, or they're flying their fixed wing aircraft directly, or they could be marrying up with strategic sea lift, and we do have some excursions that look at amphibious assault ships. So that's all coming from different ports of embarkation on the CONUS side. So the unit has to move to those ports of embarkation, and then they marry up with their strategic lift and organic lift, and they move out. And then we also have 2 MPS squadrons, as I mentioned. So there's a total of 13 ships between the 2 squadrons, and they're moving at the same time. We have an offload preparation parties that will marry up with the ships at a certain point, either at the point of origin or point of embarkation for those ships, or en route. And then they prepare the equipment and cargo to be offloaded, so it's ready to be offloaded once it comes into theater. So these are all segmented, and they're staggered in terms of timing. So with a forceful estimator, we can give the planner an estimate of when they need to be loaded and on the move to be sequenced correctly when they get to the arrival assembly area within the area of operations. So this is that arrival assembly area, more in a network topology type of view. So here we have some of the same nodes that we showed in the operational view, just kind of pulled out a lot of the other graphics. So you have a pier, you have an airfield, you have movement control centers at a couple places, and then you have some final destinations. So this is just to let you know, we have the ability to obviously change these distances between the nodes, which will expand the topology or contract it. When you get into other scenarios like distributed network type scenarios where you're looking at very small units that are geographically dispersed, you can take this same network and you pool it like taffy, if you will, and you can scale the size of the forces that will be supported at each location. All right. So I'm going to talk a little bit more about the arrival and assembly modeling approach that we're using. So once again, this is the point where the units are now into theater and they're at the ports of debarkation. In this scenario, we only have 2 ports of debarkation. We could have more. One is at the airfield, and the other one's at the seaport. And so, the people, the cargo, the equipment, all arrive either at the port or the airfield. They are processed through a movement control center and go through an assembly process in some cases. So we have the ability to basically consider things like, okay, you pull a weapon system off the ship and it needs to be up armored, or the mobile load needs to be dropped and reconfigured. So we have the ability to model that at certain nodes within this process. And then the movement control center, then, for those that don't know, that basically coordinates where the convoys in this case are going to be moved to their final destinations. And that could be to an ammunition storage point, or it could be the ground combat equipment, arrival assembly operation element. And then we have resources noted by the R's here that are basically used to pick up and move things. And those are, once again, what we want to minimize at the right size, if you will, to make sure that there's no big bottlenecks, but we're also minimizing that footprint. So I just want to show you that general model because it's very complex. If you start looking at the logical flow, the snippet of code is just for one very small part of the model. There's a much bigger modeling code in there, pretty complex. What we do, though, is we wrap this pretty complex simulation with a software package called OpDef. It's provided by Optech Systems. And it's pretty cool software where we can we create an interface with the simulation. In this case, we use ExtendSim for this one model. And OpDef helps then take control of the many, many runs that we do for that simulation. And what we can do is we introduce either a design of experiment or an optimization approach where we set multiple objectives, we set the constraints. It's using the variables within the simulation to seek an optimal solution. And it provides us some really cool output and really great discussion points with the client. And I'll show a little bit of that output later. I did want to call out a distributed network modeling approach. So this is another type of scenario that could be introduced into the same type of problem. So what I've been talking about is a MEF size scenario with a single focus and a very large arrival and assembly footprint, which is a very traditional scenario for the Marine Corps. As we get into looking at future type of battles and future concepts and scenarios, we're able to basically pull that network topology, like Taffy, as I was saying, and move those nodes different places. And in this case, just we're showing an example where you could have pre-positioned stocks ashore that are hundreds of miles away that are being used and moved using those connectors I talked about. Or you could have a long-range airbase, or you could have a tactile distribution point. And so we have the ability through other components within the force closure modeling and sim suite to model this type of scenario. It could be the same large force scale, or it could be very distributed. And in that case, what we do is we use the same approach where we wrap OpDef around a distributed network model, which has more of an optimization method versus the complex queuing model. And here we're able to accommodate basically distributed operations in a contested environment. And we use a couple of different methods and components. So I just wanted to call out this capability set packaging model that we use to figure out what are the best packages to be moved, pre-positioned and moved on these connectors based on the available transportation portfolio, if you will. And then there's a multimodal transportation packing module that we use to say, based on those available connectors or transportation enablers, how would you then pack those packages onto those enablers? So it helps with the pre-processing of the optimization method. I just wanted to call that out as well. For any of these models within the FCM suite, we have a synthesis step. And this is where, right now, we have an analyst in the loop. We have some automated methods using the R programming language to produce a really nice set of reports, either web-based or in different types of formats. So we have the ability to basically create a report. It's automated to the level that if we run a certain scenario, we don't have to really modify that report much. It's just automated. So think of all the time we spend as analysts writing reports. We've semi-automated that, mostly automated it. There are cases where you have to go back based on a specific analysis that's required for a certain type of excursions where we might have to go and modify some of the narrative. But all the charts and tables are automated, and we work that over a standard format based on what the stakeholders need. So they can go to a website view, or they can go and produce that report and share that report. And this is just to show that we do use code to do it. So there's some R code on the left, and on the right, we're able to produce multiple types of formats. So you can create a PDF or a Word document, presentation, based on how the stakeholder group needs to see it for where they are in their planning process. All right, so I'm going to start talking about some results here. And before I do, I just want to open it up. Are there any questions? And maybe, Sean, you could look for me if you see any.
Absolutely. I'd like to remind our participants, please feel free to use the raise hand feature or drop your question either in chat or the Q&A. We don't currently have any questions in chat yet, Norm.
All right, excellent. Thanks for monitoring that, Sean.
Absolutely.
Okay, so I'm going to talk a little bit about the big muscle movements of force movement. And so this is moving the force from their point of origin into the area of operation, and then when they're within the area of operation into their final destination. So we have these two types of what we call movement groups. We have air and sea movement groups. And then from there, we break down the air movement groups into what we call the Surveillance Liaison Reconnaissance Party, or the SLRP, the Advanced Party. And the SLRP is very much more a little bit of personnel, not many equipment. They're basically there to go into theater right before the rest of the force starts arriving and make sure that everything is set up. So they're the ones who have done a site survey, and they're the ones who give feedback in case there needs to be any last minute adjustments. They also come with a limited self-supporting capability. Then we have the advanced party. This is basically the opening force. So once again, the scenario that we're looking at with this MEF is a more of a benign arrival and assembly process, so it's not contested. The advanced party comes in with a little bit more people, a little bit of more equipment. They're the ones who are going to have the initial material handling equipment. They're going to set up the initial sustainment of the force so that they're ready to start receiving the force once it arrives. Another main group for the air movement group is the strategic airlift group. So these are the group that's coming in on, the different C-17s, C-130s, whatever lift is available. It could be craft equipment. And they're moving from what we showed as the different units point of origin into the theater. We have what we call a non-self-deploying aircraft. So these are the aircraft that have to be loaded onto C-17s, moved into theater. And then we have the flight ferry, and that's the fixed wing assets that are moved organically. So they basically, if they're fixed wing, they'll fly them from the point of origin to the destination. So within each of these colors, these bars, we have different colors or shadings. So we show basically movement from the port of origin to the port of embarkation, and then when they get into the port of debarkation and to when they're closed with their final units in the theater. So when you get to the left-hand side of each bar, it represents the starting point of when that movement group is moving, and then when you get to the end point, that's when the last one reaches its final destination. So we also have these sea movement groups. So we have two MPS squadrons, maritime preposition squadrons, and we have 8 black bottom ships for our baseline. And so here, what we're trying to do in terms of the objective, and this is part of the smoothing that I talked about when I was talking about the problem setup, is we want the last air movement group to be close to when the last black bottom ships arrive. So we want these to be in terms of hours or maybe a day, if we can. And so we'll go back with the analyst will help the planner go back and tweak the inputs to come up with that type of optimization, if you will. And these are based on the many runs, in this case, using the arrival assembly queuing model wrapped by OpDef to come up with these results. So this is the big picture. It takes into account force flow, the arrival assembly in theater, and when the units basically coalesce around their final destinations. Here's another example. And so I took some information off here just because some of this could be considered somewhat sensitive. So, we basically have 20 ships here. And, these are a mix of MPS ships and black bottom ships. And then what we're able to do is show the planner how the ships are sequenced. And once they arrive, once again, we have 3 berths. So you can see we start off with a group of 3 and then 3. And then over time, that group of 3 starts to, move a little bit based on the offload time frame. So there's a lot of variability in ship offloading. This is showing when the ship starts the offload based on the green dot and when the offload is finished. And those are a number of days. And so we're able to show them. And this gives the planner a really good understanding of when they could anticipate the ships arriving, when they should anticipate having their resources available, and then what's the anticipated offload time based on the resources they have available, in this case at the pier. Okay, we also can look at some output that shows us the resources within the arrival assembly area and where the bottlenecks occur. In this case, this is an example of an OpDef output, user interface output, and we caught this in process. So what OpDef does, what we're showing here is an efficient frontier as it evolves over many runs. On the vertical axis, we show airfield and pier arrivals, and then on the x-axis, the horizontal axis, we show resources, and we're trying to minimize the resources while closing the gap between airfield and pier arrivals. And so, based on many simulations runs, as you could see, we had, based on 85 simulation runs, we have a couple, and this is a simplified output. Typically, you'd see a data point for every simulation run, but that's can be overwhelming. But each one of these points represents a result of the air movement gap, or in the air and the sea movement gap, versus the resources. So, and then you could see after 170 simulations what the results were, and then the current frontier. And so this frontier is moving to the bottom left, and that's a better answer, if you will. Now, what happens with this afterwards? The analyst gets with the planner, and the planner will evaluate these different runs, and we try to group the runs that are closest to this efficient frontier. But there are cases where they will pick a solution that's off of the efficient frontier. They'll say, hey, that's a better solution for our plan. And then they'll pick that, they'll go with that. And then we're able to publish that in that FCA handbook. Here's some graphs that we show in the FCA handbook, the Force Closure Analysis Handbook, we call it. And this is, once again, available via the web, or it's available in different automated formats. This one's looking at bottlenecks within the port. So this is a seaport, and it's looking at the bottlenecks caused by the number of resources. So this is a really good indicator where we're looking at the bar chart represents the time that it's like a dwell time. In this case, that flat racks and 20-foot container equivalent units are delayed at the port. And so these are a number of hours. Seems like a lot, but you have to keep in mind there's a large volume of equipment coming in and cargo over the first 14 days of the operation. And then the dots represent the number of containers waiting, basically. So the time that they're waiting and the number. So you can see, the wait time goes to very little hours, because what's happening is the resources in the advanced party are limited because you want to reduce that footprint. And then as equipment and people come into theater, those resources are then available at the port to move containers and 20-foot equivalent units out of the port and through that multi-node process. And so you can see, even though there's more containers being offloaded, they're being processed quicker. So one of the challenges or the questions that a planner might ask the model is, hey, how much more should I put on the advanced party? How much more resources, if you will? Does that help with this or not? So we also show a bottleneck here at the port in terms of the pallets and cargo. So we're offloading 20-foot containers, and we're also offloading pallets that have cargo on it. So it's the same idea. It's interesting here. This is actually when different types of ships arrive that have pallets, more pallets than the other ships. That's why I see more of a backlog. This is interesting to the planners because then they can plan their resource and say, okay, I can expect a certain backlog, and I'll accept it for my plan because overall the force closure time is acceptable. And Sean, I just wanted to check with you to see if anybody has any questions right now, and then if I'm okay with time.
No questions yet in chat. I do have a couple questions, but I'll save those for the end. And you're doing great on time. It's we go until 1, so you got 20 more minutes
Oh,
for
perfect.
the presentation Q&A. Absolutely.
Awesome. Hey, thanks, Sean. Okay, so we're going to look at a similar chart, and this time we're going to look at the bottlenecks at the movement control centers. This is just one of them. This is still looking at the port, so we're flowing equipment and cargo in through the seaport, and then we're moving to what we call a movement control center, and this is where all the equipment is the containers and the cargo and the equipment are sorted into where they need to go for their final destination. And this is also where the assembly and up armoring would happen. So we're looking at, how many resources are needed, to minimize bottlenecks at the MCC. And so here the planner can see with this scenario and the number of resources that there is significant delay at the beginning, more than 40 hours for some days. And of course, this is stochastic, so this is an average, and we can go and look at the data to look at the variability as well, which would be a good question. And then we look at the number of things waiting to be processed. And so you can see, as resources increase over time, and this also brings in the effect of resources downstream that are moving cargo and equipment into the moving control center. It considers force flows to the ships arriving and their offload times. So it's looking at all that, and then it's looking at through this one node, how well things are being processed. So there is time, especially at the beginning, because there's a lot of infantry type of heavy equipment that needs to be up armored and configured and things like that. So there's more time up front, and then there's also effective more resources that flow in once again as the main body starts flowing in through strategic airlift to start providing more help at the MCC. So how much help can the planner get and how soon? Where should they put them? Should they put them at the port? Should they put them at the MCC? So they can look at all these different nodes and the backlog, if you will, and the wait times, and then they can figure out, okay, how might they want to adjust their planning scenario, which then becomes their future plan. All right. Kind of doing something similar. This case, we're looking at number of trips though. So, how many trips can a planner expect to move from the port and from the airfield? So I just mashed these two pictures on the same slide. Here on the y-axis, we have the number of trips from the port to the lots and the AOEs. And then we have the number of days from O-Day. And you can see that there's a big spike in, we have two different types of modes here. One is called the logistics vehicle LVS. I forget what the S stands for. That's bad. LVSR, the replacement, and the medium tactical vehicle replacement large, which cracks me up because how long are you going to have a replacement in inventory, right? It becomes what it is. Anyway, the MTVR replaced the 5 tons back in the day, and the LVSR replaced the old LVSs. But anyway, we're tracking these two modes of transportation and how many trips that they have to take. And so they're the ones that are moving the containers, the cargo, and the equipment. And so if you look at what we saw earlier as a backlog, you can see that we have some more LVSRs showing up and able to process more trips. And there's a lot of trips, so you can expect a lot of movement to move this size of force, cargo, and equipment from the seaport into the area of operations. Interestingly, you look at the airfield and you can see there's a spike at a different time frame. Actually, yeah, just a little bit different from the seaport. And here we're looking at the short bed trucks and whether they're moving cargo or passengers. So in this scenario, all the passengers come through the airfield. So you have to consider moving people and how many trips per day that you need to dedicate trucks to do that. All right, so there's a couple different ways to look at it. There's many more ways. I just wanted to show you kind of like from a resource standpoint, this whole concept of how do you minimize the amount of logistics resources and you close the force as quickly as possible what is a reasonable time to close the force? In this case, it was like, I think it was like 45, 46 days, which is pretty fast for this size of force, all things considered. A big enabler is that prepositioning, those prepositioning ships, allowing you to the force to move, mostly packs by air with some other unit equipment and some non self-deploying aircraft, but a lot of the equipment and cargo in this scenario came from the MPF ships. And then the black bottom ships bring a lot of equipment with them, so you can look at those trade-offs too. So anyway, what we showed was, for one scenario, I got into a lot of complexity with you guys. Hopefully, you were able to follow along, and then I was able to show you like our modeling approach, how we look at different types of scenarios using what we call modeling and simulation components that are all wrapped by an input and output data miner, to both accept and receive the scenario and then show the results based on the component runs. So a big part of this is being responsive to the planner's analytic needs. So there's a lot of work that we put into to try to reduce runtime as much as possible. Of course, once again, there's a trade-off with complexity. And going back to the OpDef runs that I showed you, there's a lot of simulation runs there, and each simulation run takes a couple minutes. So that couple minutes builds up when you start talking on the scale of 500 runs, right? But you have to take all that model output, be able to synthesize it well, and get that back to the planner in a timely fashion. So we use the component approach to do that. So yeah, the other big thing is, we're at a point where we've always, I think, been at a point in military operations research where, we've always been looking at, we don't just want to fight the last war, but we want to consider those scenarios in our planning, but we also want to look at the future war. And so, having a flexible way of looking at a range of scenarios and then a way to analyze those through modeling and simulation is pretty important in this day and age. So with that, I will pause for questions and hopefully provide you guys some answers.
Great. Thank you so much for that, Norm. And we do have a question in chat from Albert. So on your MCC graphs, would it be a benefit to track the human resources on site as well? How do you know from that MCC graph what resources to bring in or what to adjust?
Yeah, good question. Yeah, I did not show the number. We have separate tables that show the number of resources that back up this graph. So once again, the type of resources that we're talking about at the Movement Control Center we're looking for material handling equipment operators. And we're looking at material handling equipment. These could be based on the type of assembly. They could be everything. They could be cranes, right? You might need some low lift cranes to help assemble things. And you need material handling equipment to take cargo off of mobile loads, we call them. So when you have different types of vehicles on a ship, we have pre-staged supplies on the back of those vehicles, for example. We call those mobile loads. In some cases, the Marines want to take those off and repackage them or put them somewhere else. And so they figure all that out, and they do that at the Movement Control Center. So you need resources to lift things up. And ideally, you have material handling equipment versus 20 Marines doing it by hand. And then you have vehicle drivers, because not all the vehicle drivers are in theater at the time. So you have to have vehicle drivers standing by. You also have to have vehicle drivers with certain levels of licensing for some types of vehicles and equipment. And yeah, so those are the types of resources. I didn't show the number of resources, but what we do based on, that's a great question, Albert. I didn't provide you guys all the information, but based on which of these outputs points, if you will, that the planner selects, each point represents a whole package of resources. And so we have a group of summary tables to say for each type of unit, how many drivers, how many MHE operators, how many of each type of resources are needed to be sourced from that type of unit. And then what happens, those planners then have those numbers of people, and they could say, okay, ground combat element, that's all the infantry guys, basically, and others that support the infantry in combat support roles. We need 100 drivers from you guys. You guys need to source it. So the planner can figure out, okay, in my main body or in my advanced party, if I have positions on the aircraft for them, I need to make sure that those individuals are first. So they can start naming people, but they also know the timing of when they need to come in based on the backlog. So to answer your question, we have tables. We have tables of numbers of people that have to come in by each movement group and by each type of organization. And movement groups, just to refresh that, are back here.
Thank you, Norm.
Yeah.
And while I don't see any other questions in chat right now, because I know that somebody is typing their next question away, I'm going to jump in and ask mine. I really love how you stitched multiple tools together. OpDef, my understanding is that's extensim under the hood, unless that's something different. But OpDef, and then using R to automate the generation of those reports. And I know that time is of the essence. We regularly hear from decision makers like, I don't have months to wait for a decision. I need I essentially need the answer yesterday, right? I'm really interested if you were to develop a new scenario to then run the model and generate the results. How long do you see something like this taking to be able to inform those decision makers?
Yeah, that's a good question. So this brings up the whole, from a decision support standpoint, what part of the process does this type of capability support? And there's a couple different answers there. So let me talk about the MEF size scenario with a traditional arrival and assembly approach. Okay, so this then drives the type of scenario drives the components that we use in this force closure modeling and sim suite. And so the AQM takes longer to run just because of the complexity and the level of resolution. So in the planning process, early on, there's a couple levels of planning. One is running different sets of scenarios for what we call this force closure analysis handbook. The Headquarters Marine Corps basically runs some standard scenarios and then produces this handbook as a reference tool, kind of like a rule of thumb for planners to say, hey, if you're going to do a MEF size scenario, this is what you have to consider. These might be the results. We also have the ability then for a planner to use this to help validate their plan or adjust their plan. So they say, okay, I'll take your handbook results, but let me create my own scenario from that and let me run, and I'll hand this off to you and run it and give me the results. And we can then produce it, like I said, over the web or via the handbook. Since the handbooks is mostly automated, it's a pretty quick turnaround for that. The biggest long pole in the tent in terms of the turnaround time in this first scenario is the AQM runs with OpDef. And here's where we're squeezing down the number of resources. We're trying to make sure that the difference between the last unit, closing from through the airfield is similar, close to when the last unit closes from the seaport. That could take several days to run a large scenario through this AQM. So it's not something that the planner is going to do on the fly. They're going to do it as part of their planning process, not necessarily as part of execution. Now, what we've been doing, and with the distributed network model, which For a more distributed scenario, different type of scenario, that would take the place in this picture of where the AQM is. So we still have the OpDef wrapper around it, so the optimization wrapper. What we're able to do is run that a lot faster. So that becomes closer to like an operational planning tool, but it's still, I'd call it a planning tool versus an execution management tool, if that helps. The distributed network model runs in seconds versus minutes. So it can run many, many iterations and get an answer back within an hour versus within a couple days. Once again, the size of the scenario, the complexity drives the components, which drives, the components are based on the level of resolution required by a scenario. And then the run times are based on those components and how they handle that complexity. Hopefully that answered your question.
Yeah, thank you very much, Norm.
Yeah.
And I don't want to hog the questions. I do have another one, but I want to see if anybody else has any questions first before I jump back in. All right. Well, I am going to jump back in. That, if you don't mind, you'd mentioned this would be a good question, so I'm going to ask it. I'm very interested in how are you visualizing that variability across the runs, and in particular, you know that I'm very interested in uncertainty in these kinds of models, and so along that lines of visualizing the variability, have you considered, or have you already incorporated something like, given your goal of closing the force within 30 days, 45 days, the chance of achieving that goal is
Yeah.
X?
Yeah. There's definitely plus or minuses within some of these charts. Let me address that two ways. So I'm not the biggest fan of averages, but sometimes you need to use them. You just need some good point estimate, right? And averages aren't always the best, but sometimes they work. You also have to be able to translate the results to the planner. And the planner has different levels of knowledge of what uncertainty means and things like that. So it is a trick and a challenge to show the results while considering some variability. So in the narrative, we talk a lot about some of the variability within the results that are shown in the graphics. So, the other challenge is, how do you take many model runs and come up with the answer, right? So we've tried different methods, and some of the charts that we have that I don't show here, they will show more of the spread of results, the range of the result. And so we provide a point estimate and a variability type of statistic to show variability, or we show the range of possibilities. So we do that in some of the more detailed results within the handbook, and to address that, because we don't want to say, hey, it's going to take you 46.2 days. We want to say, hey, it could take you 46 days and a couple hours, plus or minus 3 days. So from the FCA handbook standpoint, once again, that's like published way ahead of time, saying, hey, here's a rule of thumb. In there, we have caveats to say, hey, this could be plus or minus a certain period of time. And then when we get to the actual, if a planner uses the models for their own runs, then we'll show some of that variability in the web-based output, the web-based figures graphics. It is a challenge. As analysts, obviously, if this was going to be more of a study, we'd probably show more variability in the study results, versus for an operational planner who might just get confused if we say, hey, by the way, there's this type of distribution around this endpoint, right? They might not care.
Well, thank you.
Really great, though. It's great, though. It's a really neat education when you talk about, hey, trust the model to some extent, but there is variability in the results. And so then you get into, okay, let's look at the major muscle movements, or let's look at major swings and outputs versus, if we do some excursions on the baseline scenario.
Excellent. Thank you so much, Norm. I really appreciate. I'm so glad that we were able to give you more time than the 20 minutes or less that we gave you during the annual meeting for this outstanding presentation. And on behalf of the Military and Security Society, just want to thank you for sharing your work with us today. I'd like to turn the reins back over to Alicia, and I want to personally thank her for organizing today's webinar and all the effort that she's done, and Garrett for helping with getting the word out for this this great opportunity. But I'd like to turn the reins back over to Alicia, and if you wouldn't mind sharing your slide and let people know how to connect with us, we'd love to continue the conversations going forward for future webinars and discussions as well. Thank you, Alicia. Thank you, Norm, and thank you, Alicia.
Sure, and I'm going to make sure I'm sharing my screen. So pardon me. It takes me a second. What my controls are, but I wanted to make sure that, let's see here. There we go. So yeah, so as it's been a pleasure, my first webinar hosting with you all, to be get a chance to interact. So as Sean mentioned, I am the industry liaison. And I look forward to future webinars and being able to connect with everyone. Whoops. Wanted to make sure this is how to reach us on Twitter, LinkedIn, Facebook. Obviously, if you want to email any of the officers, you can certainly do so with information below. At this stage, it ends our recording of our webinar. We thank everyone for participating and look forward to joining us for the next one coming up in a few months. Thank you.